Okay, so let's start. Just one thing, we shall meet next time in, I guess, 3 weeks, because now there are two Fridays that are free. And so as a kind of measure for preventing you from forgetting everything that you anyway forgot in the meantime, I have this wonderful idea about exercises. No, it's not as bad as you think. Just the idea is that the exercises are going to be in your charge, meaning that you, as a collective, you prepare those exercises, you divide among yourself who's doing what, or you do it all together. Doesn't matter. You can go ask me or Florian. So say Florian is assistant, so that at least he does something. You can go ask him how to solve this exercise. Then you solve it somehow, prepare it, and then you present it here for everybody. Is it okay? No, I know, but it's still better when those exercises are compulsory, like that everybody has to solve everything. This is some kind of mild version of milder. No, you don't think so? Okay, great.
Not for holidays.
Not for holidays, but you see, like there's going to be an entire week after the holidays when you can work on it. Yeah, and this measure stays. It's not like it's only for 1 week, but it's supposed to stay like this. And let's see if it works. Okay, now let me tell you what are we doing. So last time we defined some kind of nonsense called infinitesimal braided monoidal categories. So what were those? Those are like symmetric monoidal categories with first order deformation of symmetry to a braiding. So there was some kind of braiding, AB, which was symmetry, pre-composed with something which is 1 plus something like negligible. There was something like epsilon times TAB, where we adjoined this epsilon. So epsilon is somebody who squares to 0. So we modified a little bit. Morphisms were now morphisms that might depend also on this epsilon who squares in 0. And okay, this is what was the infinitesimal braided monoidal category. And what we want to do, we want to lift this condition. We somehow want to turn this first order deformation to a true deformation. So what we want, so okay, replace this first order deformation, say of beta, with a full, say, formal, with a formal deformation of beta, and we will have to deform not just beta but also gamma, as it turns out. Gamma. What does it mean? It's formal. Formal means that now this epsilon is going to be a formal parameter. So instead of having what we had there before, so we took something like hom in category C with adjoint epsilon between A and B. So before, this was declared just to be things which now depend on this epsilon who squares to 0. So this was like hom AB epsilon modulo epsilon squared. And we want to change this category. We don't want to have this first order epsilon. We want to have something which I might call h bar, say. So we define C h bar in this way, that hom of C h bar between two objects are hom AB formal power series in h bar. Something like that. And so we're looking for something like beta nu AB. That would be like this thing, sigma AB composed. It will start the same way. 1 plus, let's put here H bar TAB, and plus some higher order terms which are yet to be found. Something which is big O of A squared. And there will be also gamma ABC nu, which is this old gamma, which is not deformed in here. We didn't touch gamma. It's just gamma old ABC composed with something plus, well, we're not deforming anything in first order, so let's keep not deforming it. So plus somebody who is of this form. In principle, this is just I don't know, technical, not even technical. Just somebody decided to put here 1/2 because it's nicer with 1/2. But actually, what we're going to put here, there is a constant which we're going to call mu divided by 2, where mu is somebody from the base field, different from 0. But for the moment, it's not important. You see, the way how to explain it, if we multiply t by a constant, it still stays an infinitesimally braided monoidal category. So a little remark. So if, say, mu, whatever is in K star, then if you replace TAB with mu, TAB still gives an infinitesimal braided monoidal category. So it means that we can always, whatever I write here, we can always absorb it into definition of those TABs. Doesn't matter, right? We'll see some reason for writing this half here in a moment, but let's keep it this way. But what do I write here? I can already tell you, so just look into the future, not too far, as we shall see. And there's a good reason for that, but for the moment it's going to be undisclosed. This beta nu AB is going to be sigma AB composed, and here the thing that we're going to put is exponential of whatever is written there, so it's H bar probably mu divided by 2 TAB. Well, if our category is such that this expression makes sense without H bar, then we can maybe drop this H bar. But in general, if we're just talking about linear categories, then this is going to be just formal power series in H bar. So that's why I need to keep this. And also this gamma nu ABC is going to be gamma old ABC, and composed with whom? Composed with something of this form. There's going to be some phi, and here we put multiply this t with H bar. So H bar TAB and H bar T BC, where this phi is a formal power series in two variables, in two non-commutative variables. And this guy is called, will be then called a Drinfeld associator. And now I should close my parentheses somewhere. So this is what is going to happen. There is going to be some motivation for it. But you see, at least these expressions are sort of universal, working for any infinitesimally braided monoidal category. So it's whatever, functorial, universal, nice construction in the end, because it just uses only, there is a expression. It's not just existence statement that one can extend it, but here's a formula. It's more of this type. That's why this story is nice. Now, still a little bit of recall. We introduced those. There was this strange thing called PABA. So what was this? This thing that was a group. Well, A is a finite set. And this guy is a groupoid where the objects are just parenthesized permutations of things in A. So it's like A, B, C, D, I don't know, something. These are objects, these were objects, and morphisms were, well, if I write another object, A, C, B, D. Morphism is a braid connecting the same letters, where the strands connect the same letters. So something of this form. So these are objects. Morphisms. And why did we talk about it? It turned out, what was the motivation for that? So the idea was that if we have C, who is a braided monoidal category, one could either use just the official definition of what a braided monoidal category is. So how is it defined? It means that we have a functor going from C times C to C, and then there are those betas and gamma, beta and gamma, who are natural transformations, or natural isomorphisms, giving us rebracketing and exchange of things, giving us braiding and rebracketing. But when we start composing these betas and gammas, we get exactly things that are here. So this is somehow description in terms of generators and relations, in some sense. So these things should satisfy a pentagon plus 2 hexagons. So in that sense, these are generators and these are relations of what those natural transformations should satisfy. And when we somehow unrolled what's actually here, sort of solve the word problem, I don't know how to or geometrically describe what is happening here. So in the same way, how to say it is that's equivalent to say for each A, for each finite set A, that we have a functor going from PABA to the category of functors from C power A to C. For any object here, we're going to get a functor, and for any morphism, for any braid, we're going to get a natural isomorphism between those functors. That's what's happening here. And plus, it's compatible with substitutions. So compatible with substitutions, what does it mean? Or politically correct way how to say that it is a morphism of operads. But what are those substitutions? What kind of substitutions I talk about? When we have somehow go from CA to C, and then we also go from C power B to C, we can compose those two things in the sense that, okay, that's what's happening here. And now I plug in one of those inputs. For one of those inputs, I plug in this functor. And so we can go from this times that into C A minus one element, disjoint union with B into C. So those kind of substitutions, I mean, are just compositions of things where we plug it into one argument. So that's what's happening on the right-hand side. And on the left-hand side is structure of an operand. Same thing is in this PAB, it's just strand substitution. So we can, for objects, we just substitute for one letter, we replace one letter with entire parenthesized word, so we just plug it in. That's how it works for objects. But then for braids, what we do, we need to look at this one particular strand that we're going to remove it, but then replace it with this second braid, very thin, following this strand. So that's what's happening. It's relatively simple, and that's what it is. And the final recall, yeah, I'll probably just spend the entire lecture just recalling of what I tried to tell you last time, and then let's continue with this tradition. So the final recall, what does it look like for infinitesimally braided monoidal categories? What did we see in the same type? I already erased the definition, so there was this idea of having beta AB, who is sigma AB composed with 1 plus epsilon TAB. Now, the fact that this is a braiding can be then expressed in terms of those T's naturally, and what turned out, so okay, so it's a symmetric monoidal category plus these TABs satisfying, now say ignoring those gammas and sigmas, kind of triangular relation, the TABC is equal to TAB plus TAC, this thing. So by definition, here we require that TAB is the same as TBA. So this is definition, say, in terms of generators and relations. Well, here we were generators sigma and gamma, and here are generators, those T's satisfying just this single relation. And in terms of what kind of things we can build equivalently, now for any A, there was this Lie algebra TA that was defined as TABs equal to TBA, where now A different from B in A, satisfying some relations, some infinitesimal Artin relations that we found from there, which were that one take 4 different things, then this commutes, and that TAB is going to, because of naturality, is going to commute with TABC, where this by definition is TAC plus TBC. And finally, the right thing to do here, so this is somehow Lie. This is Lie algebra, and one can also talk about the enveloping algebra of the same thing, and that's going to have the same notation exactly, but now it's understood as a free. Here it's understood as free Lie algebra modulo those relations. Here it's understood as free algebra modulo those relations. So this is a simpler object to define because free algebra is kind of easier to understand than free Lie algebra. These are would be just words in these things. So this is just ordinary algebra, associative algebra, and then we define some linear category up A times ut A. This guy is already defined. It's what is over here, and this pop thingy are operations which are in a symmetric monoidal category. So it's the same thing as here, but now these things are no longer braids, but just crossing, so there is a unique morphism. This is as PAB, but with a unique morphism between any two objects, which you can visualize still in this way, but just those things are no longer braids, those are no longer braidings, we just cross those things. Can you imagine that? So we can also say that these are operations in symmetric monoidal categories where when we just have symmetry, so we don't care who is under and who is over, things just cross. And there is a unique way how to pass between any two parenthesized words. So this was happening here. And this additional thing, that's the thing which comes from those TABs. It just says that we have a symmetric monoidal category with additional structure. So this is a linear category, and now we're going to, if C is an infinitesimally braided monoidal category, then we have a functor going from here to home CA. C, that's when we start composing all those gammas, sigmas, and t's. We get these things acting here, represented here.
So with UTA we can also see as a category.
Yeah, right. So UTA is this is an algebra, which say in this language we see it as a category with unique object. But what this thing means basically is that now we have the same objects here as in PAP or as in PAB or in any of those. Just morphisms are elements of this. Because there is a unique morphism always here, so we just ignore that one. We always just pick somebody from there, and for anybody from there, we have a morphism. We call it morphism. Composition of morphisms is just multiplication in this algebra. Just this.
Morphisms are elements of UTA.
Yeah, so morphisms can be just identified with elements of UTA. And again, to say that we actually have an infinitesimal braided monoidal category, we should say that we don't just have these functors, but they are compatible with substitutions. And finally, what are those substitutions? Well, it should be clear here. There is nothing happening there. Or if you wish, this is the same as it was there, but is in this PAB. But since we have only one morphism always, we're not going to get a new morphism coming using those substitutions. Yeah. So this is boring, this thing. The only interesting part is this one. And what are those substitutions? That's what's written here exactly. That when we take A, TA and BC, we somehow substitute. In place of putting one letter, we put two letters here. What we should do, we define it this way. That's all. So the idea is that, so we're replacing A and B with A minus A0 disjoint with B. And what is happening is that with those generators, if you take T, A0, this guy is mapped into sum of all b's in B, TAB, and Txy is going to Txy if A0 is not one of them. Okay, so that's it. And now, to make this official definition of what a Drinfeld associator is. There is one thing I told you that, to find the deformation of a symmetric monoidal category to a braided monoidal category, we need to use formal power series in place of, just polynomials. We need to get more of them. So that's why I'm going to replace this with some kind of completion, just with putting some formal power series instead of taking just free associative algebra modulo some relations. I will take free completed associative algebra. Well, not a big deal. So let him put it this way, that U TA is graded with degree of those TABs is equal to 1. Why is it graded? Because this, sorry, I should say 0, whatever. It's graded because these relations are homogeneous. They don't kill grading. It always just says that something is equal to something of degree 2 is equal to 0. Here also something of degree 2 is equal to 0. So it's graded. And we said U TA hat, somehow completion of that, that's going to be the completion with respect to grading. So if it helps, we have a U TA is direct sum of U TA of those graded pieces. Maybe I should step with it here, I don't know, somewhere. And so this U TA hat would be then the product over all M. Of those graded pieces. But what it means in reality that we're using formal power series in place of non-commutative formal power series in place of non-commutative polynomials. And I will still keep this. And the final, so this might not be, say, yet so surprising. So we're looking for the new beta and new gamma as things that live in here, where for new beta it would be where A has just 2 elements. For new gamma it would be something from here where this A has 3 elements, those 3 objects that we want to, where we want to act. The thing that will come now might be a bit surprising, but it makes things way nicer. So then we finally take the group TA in sitting inside of this U TA hat. That's what is exponential TA, so some of the Lie group corresponding to this Lie algebra. Anyways, this Lie algebra is infinite dimensional, but it's still a pro-nilpotent or whatever is the right word, so this makes perfect sense. Just it's defined in this way, that elements in here are exponential of elements who are there. If you wish, another way how to say it, these are group-like elements of this UTA hat where the coproduct is defined. Group-like elements, no, just, yeah, I'm maybe using words that you probably heard, but maybe you didn't want to. Or is it okay if should I explain, should I say again what is group-like? Yes, I will, okay. So, ES, what does it mean to be group-like? Well, first of all, there is a coproduct. We have on the enveloping algebra of any Lie algebra, there is automatically a wonderful, nice canonical coproduct defined for coproduct delta, going from UTA to UTA turns UTA. And if I complete things, then I probably have to complete this tensor product to be politically correct. But it just means that like formal power series now in these variables and those variables which commute with each other or something like that. So the coproduct given by is by the fact that delta of those defining elements are primitive. That they satisfy one tensor TAB plus TAB tensor 1 and group-like. So we know it for the generators, and then for anybody else, we just use the fact that coproduct should be a morphism of algebras. So we just then use the fact that delta of, I don't know, xy should be delta of x times delta of y, where the product is taken in this algebra with the tensor product of this with that. And group-like means that delta of whatever x is equal to x tensor x. And these are the same things.
Is it easy to show?
It takes a bit of time, but yeah, so it's easy to show. Okay, cool. And now this is a nicer thing than that, just because I even know how to write it. I don't know how to use this fracture T, so I'm using this strange thing, and there is this U and head and whatnot. This is just, and also this is a group, so let me just use this. So that's the main reason for introducing this stuff. Perhaps a little example. So first of all, who is, say if A is just AB. So first of all, who is TA? It should be sort of stupid, but we should just realize what are those definitions that I just erased anyway. But so TA is generated by what? It should be generated by all TABs, but there is only one AB here, which are already called AB anyway. So this TAB, and the relations, there are no relations here. There are just no, each relation uses at least 3 different things, or one of them uses 4 different elements of the algebra of this set. Nothing here, right? So it's just this, well, K, it's like, as a Lie algebra is one-dimensional, so whatever is our base field, it's just this guy. So U, TA, in this case, are going to be polynomials in the same stuff. Sorry, polynomials, I said. Now U, TA hat are going to be formal power series. Sorry, T, A, B. Oh, yeah. formal power series, and this should contain our TA. What are those things? Those things are going to be things of the form, well, it should be exponentials of things from here. So exponential of, I don't know, lambda times TAB. Lambda is in K. And as a group, is just K with plus. So this is equal to K, or isomorphic to K plus. Not too much, right? If things get more complicated for once this A increases, but we have to start somewhere. Okay, and now I can tell you it's right time to tell you what the official definition of a Drinfeld associator is. So definition. Drinfeld, let me spell him out. Associator, say, of weight mu, who's supposed to be non-zero, so K star is whatever A. Well, I should write it like this, like morphism of operands, which goes from PAB, this T, that is, what does it mean, the morphism of operands? That means that we have a functor or, if you wish, just morphism of groupoids. Which goes from P, A, B, A to TA, and this is for any finite set A. And this functor is supposed to be compatible with the operand structure. Functor, let me call it, I don't know. This one maybe is small phi. This is supposed to be phi A. So what compatible with operand structure means that, well, first of all, it's functorial under just bijections of those A. So if you just rename things in elements of A, then you only rename elements of A. And it's most important, it's compatible with those operatic substitutions. If we do substitution here, we should do substitution there. But where is this mu? I forgot mu. Such that when we take phi, but let me just use this phi always, so because A is going to be clear, we say, and so this guy, you see, now we're in PAB of the two-element set AB. This is a particular morphism going from this object to that object. That's the outcome should be somebody sitting in here, right? So it must be of this form. So there is also only this lambda who is undetermined, and it should have something to do with this mu, and such that this thing is going to be exponential of, and here for some reasons we would put mu divided by 2. times TAB. That's the end of the definition. And say maybe one little remark, why would one ever write mu divided by 2? Possibly the reason is that then phi of this full thing, full twist, and this guy is going to be exponential of mu TAB, so that's why for half turn we put there 1/2 so that we can have 1 for full turn. I'm not sure whether it's worth it, but that's how that's the convention that Drinfeld was using, and one should keep the convention. Okay, so that's what the Drinfeld associator is. It's probably difficult to penetrate right now what it is. So after the break, we shall have a look at it, and we'll see there is something very concrete, and we shall look at how to find equations that this stuff should satisfy. Okay, so let us now try to understand what this means in concrete terms. Maybe one little thing, I already told you about it, but let me say it again, maybe in different words. There is this silly mu here, and as I said, it doesn't matter what kind of mu is there. We can always get rid of it. The way how to get rid of it in maybe official terms is that a little remark that if, I don't know, whatever, lambda, say, lambda is in K, let me start. It works for 0, but then it's not an isomorphism. Then if we send TAB to lambda times TAB, this gives an automorphism of this, of those TAs, also TAs, and all other things, which is compatible with operatic structure. So if we wish, it's an automorphism of the operand T, and we can always compose. So if say phi is a Drinfeld associator of weight mu, then when you do this pub T, here put this phi, and here we do this TAB map to 1 over mu TAB. So this thing is going to be a just composition of these two things. Just doing this and then doing this silly thing just of replacing TABs with TAB divided by mu. So this composition is a Drinfeld associator of weight 1. So when it comes to this weight, we can move between different weights very easily simply by rescaling those TABs. That's all that's happening.
Can I ask,
Yeah.
does this big T have a name?
Okay. We call this was called Drinfeld-Kono-Lie algebra. So we can call it Drinfeld-Kono-Lie group, if you wish. Otherwise, it is named T. It's shorter, so better. Okay, now, say Drinfeld associators in concrete. So let's try to work out concretely or say, to see some equations, understand what it means. So first of all, this PAB thing is generated by well, how to put it? Well, on okay, let me put it. Let me write it here. So this is what is called beta AB and gamma ABC. ABC, ABC. And on picture, when one usually tries to indicate this bracketing by putting things close together, those that are parenthesized, they're being put close together, but it starts failing when there are too many parentheses because there is not enough space, but here one can do it. So this is just the identity braid, but still I draw it this way because it's supposed to say something. So it's generated in the sense of as an operator. As an operator. That means that we can get any morphism by composing these morphisms, or you can compose them in the groupoid, but you can also use those operatic substitutions. So using these things and using that strand substitution, you can obtain everything. Like for example, well, you will always have there just identities, so you can always say just double one strand. It's fine. Or you can or you can replace one strand with this thing again. You'll get some braid with 3 strands, etc. So what is this statement? We actually saw this statement. This is exactly the statement that braided monoidal categories are defined in terms of betas and gammas. It's enough to say that there is a beta and there is a gamma. And once we start composing these betas and gammas, we get everything. Every morphism that can be obtained by composition of betas and gammas is obtained by composition of betas and gammas. And then we said that those morphisms, well, they are given exactly by those parenthesized braids. Now I'm just invoking back that those parenthesized braids, they can always be obtained just by using this or that. This is only for reparenthesization, so if we forget about parentheses, we can forget this. Every braid can be obtained from this one just by strand substitution. Okay, so since it's generated by these two things, it's enough to say what is the image of these two things. So phi is determined by the image of this guy, and we already know what it is. It's exponential of mu divided by 2 TAB, and by phi of the other thing. What do I call it? Gamma ABC. And this is going to be called capital phi, and it lives in P, A, B, C. That's where it is. So this is the only unknown thing that we need to understand. It's something that should satisfy some conditions. And let me come back here again. So this thing is generated by beta and gamma. And what are the relations that these things satisfy? They are exactly, just recall what is the definition of braided monoidal category. So we have this and that satisfying pentagon and two hexagons. So by this, modulo pentagon and two hexagons. So when are we going to get a morphism of operas? If and only if the image, well, this guy and that guy, together they satisfy pentagon and hexagon. And I'm going to write it down now. And I'm sorry, I need to, well, I should have been using paper all along. Maybe that way this course would be worth something, but now I have to do it because I cannot remember these things. So say pentagon. So what was it? It's, we have A, B, C, D. I guess say it's not necessary to remember everything here, or maybe it is necessary, but I don't remember anything from there. So. But it's just to give some idea that those things are fully concrete. One can write it down and it's doable, and look it up or something. So the Pentagon relation is something like this. So we go from here to A, B, C, D, and from here to A, B, C, D, like this. So this is a relation satisfied in that PAB. Okay. In PAB, what was it? A, B, C, D, I guess. So composing like this is the same as composing like that. The same relation should be satisfied by, well, we're using here only gammas. So all of those arrows are some gammas. So, yeah. So all of those arrows are going to be sent by little phi, are going to be sent to some forms of those capital phis. And we should get some relation satisfied by those capital phis. And let's read them off. So who is this guy? You see it's re-bracketing when we take A, B, and then CD as a single object. So I'll write it this way. So how should we understand this? This is that thing. First of all, it belongs to T, A, B, C, D. And what is it? It is, how do we obtain it? We take somehow phi, the thing who lives here. Let me maybe call it, let me put here A, B, C. Doesn't really matter, it's just remembering names of those letters. And what we do here is that we take this phi A, B, and I don't know, say X. And then make operatic substitution, apply substitution X, or replace X with CD. But what does it mean in concrete terms? It just means that this phi is going to contain all those T's, right? So phi is an expression in T, I don't know, IJ. So what does it do? It does that TAB goes to itself, TAB, TAX goes to TAC, TC plus TAD, and TBX does the same thing. TBC plus TBD. Okay. It's just the same thing as here. We only replace these two things with those sums. That's what it means. That's what's happening here. Now let's do the same thing here. Here, so what's happening there? AB is understood as a single thing. So it's phi AB, C, D. And that's supposed to be equal going that way. So I, again, need to start at the end. And I'll just write it from here. So it's phi B, C, D. Phi A, comma B, C, comma D. And finally, phi ABC. So this phi ABC, that's what's happening here. We are not touching D, we're only doing this thing. So all of these are understood then as elements of this guy. We'll see this ABC. Well, okay, it just doesn't use this fourth letter, D. Nothing's happening here. Just when there is some doubled letter, it means that you need to replace the corresponding variable with this doubled thingy. So you have to somehow imagine that this is somehow TA and comma CD. That's what is somehow using. Just one needs to use the right variables. And we have like this TA, comma CD, and that's all. So this is the Pentagon relation. This is the most difficult relations of them all. I will box it, even though I'm not able to really memorize it, but this is a thing that it should satisfy. Now, let's have a look at those hexagon relations. So how did I write it like this? A, B, C, A, B, C, so this is gamma, this is now some beta. Here I'm jumping with that guy, so B, C, A. And now we're going to BCA. So this is big gamma again. And here we should apply beta, so it would be BAC, then gamma. So that should be B, the same order, just different quantization. And here we apply beta. Okay, so this commutes in now this parenthesized braids with 3 strands. We apply to it this phi. And what do we get? Okay, this gamma is sent to some phi, that is sent to exponential, that's the phi. Okay, so let's write it here. So this is going to be phi, and you see what's happening is just B, C, A, B, C, A. No doubled letters ever here for gammas. It's just some permutations of those letters. Now this beta, that's beta between A and BC. So that's being sent to exponential of mu divided by 2. And now there's going to be TA, comma, BC. Or if you wish, I can rewrite it what it means. This is TA, comma, BC. the thing that was happening here, that when you see a doubled thing, you just need to do this substitution. So this thing is TAB plus TBC. And times there is another associator happening here, which is just ABC. And it's equal to, and now possibly I can do it even without paper. Let's see. So it's exponential mu over 2 TAC phi BAC and exponential mu over 2, that's happening here. It's only doing it between A and B, TAB. Okay, that's it. So this is hexagon. And then there is another hexagon, but this other hexagon differs just by making the opposite braiding. Instead of going under, we go over, or something like that. So the other hexagon is this thing that where we put here minus. So also for when you replace mu by minus mu. Those are those two hexagon things. Now this is still, this pretends to be concrete, but it's still horribly abstract. Because, well, why is it? Say these things that they are reasonably concrete, exponential of a variable, yeah, sure. But this phi who lives, okay, that's somebody who lives in this guy. What's this guy anyway? So let's have a look. Let's now try to understand what this thing means. So next question is somehow what is this TABC? Or if you wish, what is U of the same thing, ABC or TABC? So let's have a look at definitions. What is it? It's generated by TAB, TBC, TAC. And then there is only one relation really. Or whatever, the relations would be something like this, that TAB commutes with what? Commutes with T AC plus TBC. So this is equal to 0. Sorry. The guy is equal to 0. And there are two more. So, and also we can cyclically permute those letters. So it's true for any pair here. But I can write it in the following way. Exactly the same thing is that if I said that Z is equal to sum of all those TAB, so TAB plus TAC plus TBC, then those relations are what now? That see TAB commutes with Z. Why is it? Because, well, this thing is Z, there is only one piece missing, but which is the piece missing is TAB. TAB commutes with itself. So this is a relation that TAB commutes with this guy. Also, TAC commutes with Z. And if you use also TBC commute with Z. So we can rewrite this thing in the following way. Hence, so I'll be using, here we're using these three generators. I can replace one of them with Z. Any one I wish to take. So I will take generators. I will keep TAB and TBC. And then there is this Z thingy which commutes with everybody. So it's central, it's just K times Z. So this is a small Lie, free Lie algebra. So this guy is a free Lie algebra on these two generators, and plus this central part, just this thing. So it's not so bad. Also then, U TABC would be free algebra generated by these two things, TBC and tensor. Easy. Okay, and now this, let us have a look at this phi. How do I want it to say it? Like this. So also if I take this way, then we get something like this. And now our phi, I know ABC, that sits in here, or rather it sits in T ABC, who's a part of that guy. So therefore, what are these things? These are somehow, that's going to be a formal power series in two non-commutative variables, TAB, TBC. And there is this additional thing, and since our phi is supposed to be group-like or exponential of somebody, so it's supposed to sit in here, right? So it's going to be of the form this times exponential of, say, lambda z for some lambda. That's already not so bad. These are relatively concrete things. So there is non-commutative formal power series in two variables. It sounds reasonable. Then there is one additional thing. So next thing to see is that we don't need this lambda. That lambda is just equal to 0. So in fact, lambda is equal to 0. So we should be able to see it from pentagon and those two hexagons. But as a surprising move, well, we know that the pentagon and hexagons are equivalent to this PAB thing. It's the same thing. I'll just use directed as PAB. Why not? So how to see it? You see, what is that phi? Phi is obtained, we take this lowercase phi and get phi ABC, ABC. Now we can do arbitrary, well, phi is a compatible with operatic substitutions. So let us do some particular substitution, and we shall substitute what? We shall substitute this B. I mean, we have to replace this strand with some other braid, and we replace it, this is the surprising move, we replace it with empty braid. So substitute so this was so far maybe undisclosed, but empty set is a finite set. So that thing, this makes sense. It contains a unique object. Which is just empty word. It's just that it's nothing, but it's unique. And also with the unique isomorphism, unique. And this unique object, this is what corresponds to the unit of in braided monoidal categories. So unit in braided monoidal categories. So let's do it. We substitute this empty thingy, and we get what? This guy, just the identity, right? On AC. So we have to send it to 1, right? Identity is sent to identity. It's a groupoid morphisms. Identities are sent to identity. So it needs to be sent to 1 in TAC. But what is that 1? How do we obtain that 1 here? So that should be somehow the same as phi A, and here this nothing. We put here this nothing, empty thingy, and B. But what does it mean? What does it really mean? It means that C. Yeah. It means that we send TAB, we replace B by nothing. This becomes 0. TBC becomes 0, but TAC becomes itself, TAC. That's how we're getting, so this belongs to ABC. That's how we go from here to there. We kill these two things, but we keep this one. And if you look at what happens now, in this case, well, so this F, TAB, TBC, exponential lambda Z is mapped where this guy is replaced with 0, this guy is replaced with 0, so we just get F evaluated 0, 0, which is equal to 1, because it's a group-like thing, so it has to be equal to 1. This becomes 1. And this in this Z is the sum of all these three things. 2 of them will just die, but the third one remains. So this one is mapped to exponential of lambda times TAC. But it has to be 1. We want to have 1. So lambda is equal to 1. Sorry, not 1, 0. Yes. Thanks. So our associator is in fact just a non-commutative power series in 2 variables. That's already a reasonably nice object.
So can you also say that from this that the first coefficient is 1?
Yes, you see the first coefficient has to be 1 because it's a group-like thing. It's phi is exponential of something. Exponential of something from this t thing. So it's going to start with 1 and plus things containing those t's. So that's why it's necessary. That's why it's necessary with 1. Okay, so what we can say now, so we see that phi ABC, well, is of that form. So it's an exponential of some Lie series in TAB and TBC, but it sits inside this K TAB TBC. Exponential of Lie series just means that it's group-like. It's the same thing. So somebody from here who is group-like, and the usual notation is that instead of this f, one actually uses that phi. So the phi itself is called this exponential, this power series. That phi is equal to phi ABC is equal to phi TAB TBC. So just this capital phi now replaces that capital F. So this is what was F just before. Maybe some other things that we can do. Oops. I decided to delete this middle strand, but I can just as well delete this outer strand or this outer strand. I can substitute it's empty braid either here or there. There's no problem. So it should one should get the same thing. So a little remark. So if we substitute the empty braid for A or for C in ABC, what do we get? We still get identity. Well, if I substitute for A, we get just identity on BC, or identity. If I substitute here, we get just identity on AB. And what is the outcome now? If we already know that phi is of this form, but if we do this stuff, what does it do? If we delete, say, A, it will kill TAB, and this guy will remain, etc. So what it implies? What you need to remember, so that phi is exponential of something, I don't know how to call it, L, TAB, TBC, where this is a Lie series, meaning it's a series just written in terms of commutators of things, nested commutators of things. And if we kill, say, TAB, what happens? Well, certainly, with kill meaning that I just substitute that it's equal to 0. Certainly, any commutator containing the TAB will vanish, will just go to 0. The only thing that will possibly not vanish is when there is just TBC alone, not commuted with anybody. That's the only thing that might possibly survive. The same there. So it doesn't tell us too much. It just tells us that this L doesn't contain linear terms. And so L has no L has no linear terms. It means it contains only commutators. And what one can say, in fact, from there we can already see that phi, that means variables x, y, it's exponential of a Lie series which contains no linear terms, so it certainly starts with 1. Then there might be something containing some coefficient here which contains a single commutator, and then there would be some higher degree terms. And what's happening here, there is a number that one can compute, and it's mu squared divided by 24. And why is it mu squared divided by 24? Because it's an exercise. So one of exercises is that this term is fully determined. It's mu squared divided by 24. It's only the rest when the fun starts, in some sense.
Is there a minus?
The exercise is also to find out whether there is a minus.
Yeah.
Okay, we have just a couple of minutes left. We replaced, we just found out that this associator itself, this phi, is a relatively reasonable object. We know where it where it's supposed to live. That it's just non-commutative power series in two variables, having some nice properties, like being exponential of a Lie series, maybe not having a linear term, so starting with at least with one commutator. And then it has to satisfy all those strange relations, this pentagon and two hexagons. And as the final thing, we'll not have, let's see whether we have time for doing something with it. If not, then these are certainly going to be exercises, just to plug in things that use what you know, maybe come to ask somebody how to do it or something, if necessary, I don't know. And, well, let's see. So this phi satisfies, well, it satisfies pentagon and two hexagons. That thing is for sure. But those two hexagons then can be rephrased into some nicer forms. One thing, there is some reasonable relation that phi yx is equal to phi xy inverse. It's one thing that one can compute. And once we do it, then we don't need to keep two hexagons. There is only one hexagon that remains. And I try to compute it, and when I try to compute something, it's mostly wrong. But let's see. I'll write it down and the exercise to find out whether it's correct. Or
So this one is implied by the...
yeah, this one is implied by probably just those two hexagons I don't have. And so one can, but there is still one hexagon remaining, so we cannot kill both hexagons just with this one relation. So, but this other thing is, okay, I'll write it down. This is what I computed. xy exponential mu divided by 2x phi zx exponential mu divided by 2z and phi yz exponential mu divided by 2y is equal to 1, where z is equal to minus x minus y, or if you wish, there. It's already nicely symmetric, so it's like the relation is that x plus y plus z is equal to 0. So we have three variables bound by this single relation. Then this stuff is supposed to be supposed to be 1. And now this, that thing, plus the pentagon are equivalent to saying that phi is an associator. And those make some, well, exercises will come with hints. So it's not just stare at things, how do you find out? So there are nice ways how to come up with this. But this is simply just hexagon written down. You see, it's always like phi, exponential phi, exponential phi, exponential. There are 6 terms. So there is nothing really happening here. Maybe sometimes this relation was used there to simplify things a little bit, but this is maybe the more surprising relation in some sense. Okay, and so I should end. What I can, now the main thing, I will not even write it down, is now to show that there are associators, that we can find an associator. Once we have it, we can start deforming our infinitesimally monoidal categories to braided monoidal categories and Poisson algebras to non-commutative algebras and everything like that. But for that one is to now wait 3 weeks. Okay, thanks. T A comma BC as being equal to T A comma B plus T A comma C. That's the operatic structure. That's what enters here. So the idea is that T A0 maps to, now I replace this A0 with the product of those things entering. So I need to take the sum of all of those. So it's going to be sum TAB with all B in B. And now let me call it a T. I know I need some string letters, whatever. Alpha beta. Alpha beta goes to itself. T alpha beta if this A0 is not one of those. Alpha beta. And so that map is compatible with this operatic structure. Okay. So that's all for today. There were not yet any Dreamfield associators, but that's where we start next time.